As you can tell, we started a new unit, and probability is the study of chance, and we need a mathematical method to describe the likelihood of an event happening or not happening. Oftentimes we have to do an experiment to figure out what the probability of something happening is, like was in the case of tossing the drawing pins, because there was no mathematical similarity in or no geometric similarities in the pin. There really isn't any way to find out the probability of the pin landing on its back or its side other than by experiment. And the more trials you have, the closer you're going to get to the actual probability. So there's a few important definitions you're going to need for probability. And pardon me if you already know them, but trials, that's the total number of times an experiment is repeated. Outcomes, that is the different results that are possible when you perform a trial of an experiment. Frequency, that's the number of times a particular outcome is observed. And relative frequency is the number of times a particular outcome is observed divided by the total number of trials. So we're going to put frequency divided by total number, oops, that's an O. A couple of other things that you need to know are sample space. That's the set of all the possible outcomes of an experiment. For instance, if I am tossing 2 coins, then my sample space would look like this. It's a set, and I could get head, head, heads, tails, tails, heads, and I could also get tails, tails. So this is an example of a sample space. Complement of an event, that is everything the event is not. So if I say that C is an event, call it event C, then the complement and we write that as C naught. Okay, C and C naught, the probability of C plus the probability of C naught is equal to 1. It's everything that C is not. So, for instance, if I am tossing a coin and I say what's the probability of tossing a head, the complement of tossing a head would be tossing a tail. Okay, so there are different ways to represent the sample space. So for a coin toss, it would be heads and tails. It's just making a list. So listing is one way. Rolling a dice, that would be 1, a 2, a 3, a 4, a 5, or a 6. We can use two-dimensional grids to represent a sample space. So if I'm rolling 2 dice, I could roll a 1, a 2, a 3, a 4, a 5, or a 6. And the other dimension would be 1, 2, 3, 4, 5, and 6. And then I'd make a grid. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and 6. All right, so if I wanted to know what represents the sum of rolling 2 dice and getting a sum of 9. Well, if I roll a 3 and a 6, I get a 9. If I roll a 4 and a 5, I get a 9. If I roll a 5 and a 4, I get a 9. And if I roll a 6 and a 3, I also get a 9. So this represents getting a sum of 9. And if I wanted to calculate the probability of rolling a sum of 9, you can see here that there are 36 different intersections, and 4 of them are 9. So that represents getting us that represents the probability. All right, you try. I want you to draw a 2D grid to represent 2 coins tossed. And then show me where the representation of tossing 2 coins is getting 2 tails. Pause this and restart it when you're ready. Okay, yours might not look exactly like mine, but I need 2, but it should look similar. So I'm going to call this heads, tails, and heads, tails. Yours might be the opposite, that's okay. And if I wanted to represent where, you can see I have 4 different outcomes here. 1, 2, 3, and 4, that's all the intersections. And if I am looking for where what represents tossing 2 tails, it's where the 2 tails intersect, right there, which would be 1 out of 4. The probability of 2 tails would be 1 out of 4 because it's one possible outcome over 4, one positive outcome over 4 possible outcomes. Okay, another way we can represent probabilities and sample spaces are to draw a tree diagram. This one is a little bit longer example, so bear with me, but I'm going to represent drawing 2 marbles from a bag, and the bag contains 3 marbles. It has a red, a yellow, and a green marble. So to draw a tree diagram, I have to draw the outcomes that happen from the first draw. And since there are 3 marbles, there's going to be 3 branches, okay? And so it could be either a red marble, a yellow marble, or a green marble. And so this represents event 1. Event 1 is drawing the first marble. And since there are 3 marbles, and they're all the same, there's an equally likely probability that I would get any of those marbles. Third chance that I'd get a red, a third chance that I'd get a yellow, and a third chance that I'd get a green. You'll notice that all of these probabilities here, where's my laser? There it is. 1/3, 1/3, and 1/3, they all add up to 1. Okay, now I'm going to take and add to my tree diagram I'm going to represent the second event, which is drawing the second marble. Well, I've already drawn the red marble here. So all I have left to draw is either yellow or green. Okay, so this represents event 2. At the end of my branch is event 2. And since there are only 2 marbles left, I have an equally likely chance of pulling up either marble. If I draw the yellow marble on the first draw, then what I have left is red and green. Also equally likely to happen. And then if I draw a green marble on the first one, all I have left are red and yellow. Also equally likely to happen. So you'll notice that each individual section of the tree, all these probabilities add up to 1. Okay? Now if I want to calculate, or I'm going to list the sample space now. And in order to do that, I need to go down the branch from the base of the tree. So I'm going to go down the branch here. If I draw red and yellow, this is my red, yellow. I could draw red and then green. I could draw yellow, then red. I could draw yellow, then green. I could draw green, then red. I could draw green, then yellow. And those are all my possible outcomes. This right here is my sample space. If I wanted to calculate the probabilities for each of these events, well, I have to think about the probability of red and then yellow for the first one. Since it's an and, I multiply together. It's going to be 1/3 times 1/2. And that is from the and. This and that have to happen, and that's going to be 1/6. And if you think about it, all of these are going to be the same because they're all 1/3 times 1/2. So the probability of red and yellow is 1/6, 1/6, 1/6, 1/6, 1/6, and 1/6. Pretty easy, right? Easy enough that I want you to try drawing a tree diagram to represent spinning a spinner. The spinner has sections A, B, and C. They're all the same. They all have the same size so that it's equally likely. And then the second event is flipping a coin. Stop this, and when you're ready to check your answer, restart it. Okay, so the first event has 4 possible outcomes. I could spin an A, a B, a C, or a D, and these are all equally likely. You know, sometimes these aren't equally likely, so these branches won't always be the same, but that's for another day. All right, and then the second event is tossing a coin. So no matter what I spin on the spinner, I could flip a head or a tail no matter what. And you'll notice that I have 1, 2, 3, 4, 5, 6, 7, 8 different possible outcomes, and they all are equally likely. But if I want to list the sample space, I could do an A and a head, an A and a tail, and the same for all the others. And the probability of flipping a coin as head or tails is 1/2. So all of these are 1/2. So the probability of A and head, you get my drift, is 1/4, and is multiplication, 1/2, so 1/8. And that makes sense because we have 8 equally likely outcomes. So the probability of all of these is 1/8. All right, that's it for today. Hope you learned a little something about probability.